Alright guys, so today we're doing another LeetCode question, and with this particular question, it's important to me because I actually just had a mock interview, and my interviewer asked me this question, and during the interview I came up with the naive recursive approach, but I was actually informed by my interviewer that, the optimal solution to this problem uses dynamic programming, and, during the interview I was completely stuck. I didn't even know how you could develop the intuition to come up with a dynamic programming approach. I was very confused, and overall I did really bad in the mock interview, which is why I'm making this video right now, because I want to show you guys so you can so if someone asks you this, you can develop that intuition and you don't make the same mistake that I did. So yeah, let's get started. So in this problem, we are climbing a staircase. It takes n steps to reach the top, and at each point, you can either climb one step at a time or 2 steps. And we're asked, in how many distinct ways can you climb to the top? And so let's see these examples. If we're given 2 steps, there's 2 possible ways to climb the staircase, because we can either just take 1 step at a time, or we can just take 2 all at once. And then in the second example, again, we can either take 1 step at a time, or we can take 1 step, then 2, or 2, then 1. So it is important to note that these 2 options are different from one another. So yes, I want to help you guys develop the intuition to see why you would use dynamic programming here. So let's start off with some examples. So let's say that n equals 0. So, let's say you're run into this situation where there are 0 steps to climb. How many unique ways can you climb this staircase? So, let's see. So, if we have no steps, essentially we have 2 options. We can either take 1 step, or we can take 2 steps. Okay, so if we can only take 1 or 2 steps, and there's no steps to climb, how many ways can we climb 0 steps? And the answer here would be 1. Now, you might think the answer would be 0, right? But if you think about it, if there's no steps to climb, you really only have 1 option, and that is to just not climb the steps at all. And so essentially, right, we have 1 choice. Let's do another example. Let's say that n is 1, right? Again, if n is 1, we have 2 options. We can either take 1 step or 2 steps. Okay, how many options do we have? Right? Can you see why the answer would be 1 again? The answer is 1 because we can't take 2 steps. There's only one step in our staircase. So, how is it possible to take 2? All we can do is take 1 step. So, just from these 2 examples, we can kind of get an idea of what our base case would be, right? So I think it's important to jot down for our base case. If n is 1 or 0, just return 1. Cool. And so I mentioned dynamic programming earlier. So to show you the dynamic programming approach, I want to start off with a bigger example. So, let's leave our base case up here. So that's our first finding. Let's say n is 4, right? Let's say n is 4. We still have 2 options. That's not changing, but we don't know what our answer is going to be yet. Okay, for our answer, we're going to use dynamic programming. So, what is our DP table going to look like? Well, our DP table is going to be of size n plus 1, and you'll see why in a second. So, first, create a DP table of size n plus 1, and you will see why in a second. So we have our DP table. Cool, right? So essentially what we're going to be doing here is we're going to be taking the bottom-up approach here. So, you could either do this top-down or bottom-up. So with this bottom-up approach, essentially we want to ask ourselves, okay, what were the two previous results of our past subproblems? What were the answers to our past subproblems? And this is what I mean. If we're at index 0, okay, if we're at index 0, how many ways are there to climb 0 steps? We said 1, right? So after we create our DP table, we're at index 1, we fill in a 1 right here because there's only one way to climb 0 steps. And we also found if we have 1 step, there's just one way to climb 1 stair. So just put a 1 right there. Alright, so if the number of stairs is greater than 1, right, this is where we have to do a little bit more thinking. So how are we going to get these past subproblems? Well, really, if you understand that we can only take 1 or 2 steps, essentially what we want to do, we want to get the result. We want to get the result of climbing 1 step, and we also want the result of climbing 2 steps, right? So let's say in this example n is 2, right? So far we have our previous subproblems. So if n is 2 and we can either climb 1 or 2 steps, that tells us that we want the answer to the subproblem of n minus 1, climbing 1 step, and we also want to add that to the subproblem of n minus 2, 0 steps. So if you add n minus 1 and you add that to n minus 2, you would get 2, right? Because at this point n is 2. Similarly, if we have 3 steps, how many possible ways can you climb 3 steps? Well, we know it's the result of 3 minus 1, climbing 1 step, plus 3 minus 2, climbing 2 steps, right? So essentially we'd get 3, because climbing 1 step would give us n minus 1, which would be 2, n minus 2 would give us 1. And finally, when you hit the end of the DP table, right, you add up each of these subproblems, okay? By the time you've added up each of these subproblems and you're at the last index, you do the same process. What is n minus 1 plus n minus 2? It's just 3 plus 2, which gives us 5. Okay, so this last slot in our DP table will be our answer. All we're doing, guys, we're just taking each of these small subproblems and we're piling them on top of one another. Okay, if there's 0 steps, one way to climb 0 steps. 1 step, one way to climb 1 step. Once we get to 2, right, we add up all of our previous subproblems. We add 1 plus 1, that gives us 2. Once we're at 3, we add the previous subproblem we computed, okay, plus the problem before that, okay, which is why we did 2 plus 1 to get 3. Same for 5. Our previous subproblem we just got was 3, okay, so we add that to the subproblem before that to get 5. So our answer in this case, when n is 4, would be 5. So yeah, guys, that is the dynamic programming approach. Let's go ahead and write that up. So it's going to look like this. Interarray DP equals a new interarray of size. We said n plus 1, right? Because we have to account for that extra slot where our answer is going to be. So it has to be n plus 1. And what we're going to do is we're going to loop through the entire DP array, sorry. And so Let's do that. dp.length. Cool. So essentially what I'm saying is start with 0 stairs. Okay? So if I is less than or equal to 1, what does that mean? That means that we're either climbing 0 stairs or 1 stair, which in that case we would just return 1, right? That's what we said here. That's the first thing we found. Same thing here when n is 4. If I is 0, give it a 1. If I is 1, give it a 1. Otherwise, we want to mimic climbing 1 step and then climbing 2 steps, right? We want to solve our subproblems. So otherwise, we want to return 1. Rather, dp at I would be 1. Sorry. Otherwise, dp at I would just be dp at I minus 1, climbing 1 step, plus dp at I minus 2, climbing 2 steps. Same thing we did down here. And then finally, our answer is going to be in that very last slot of our dp table. So all we really need to do is just return dp at n, because that's our final spot. So let's run this, make sure it's all good. And so it looks good so far. Let's submit. And we're good. So yeah, guys, getting the intuition for these dynamic programming problems it's pretty tough. It takes a lot of time. I'm still learning myself. I have a lot to go, a long way to go, but you know, practicing these problems really does help. And I also hope this solution was clear to you guys. This explanation was good. And yeah, I hope to see you guys in the next one. So thank you.